rather than just do the online revision session to the people who turned up to it, I'd share the main points that we did from the presentation as we went through it. So looking at biomechanics, we started off with Newton's laws. For each law, I've highlighted the key things that you need to know. So with Newton 1, it's important that we both know how it applies to an object at rest and also an object in uniform velocity. And they change because of this unbalanced force. We'll talk about unbalanced force a little bit later. With Newton 2, we look at the change of momentum, so not speed or distance. It is actually change of momentum, and then the size of that is proportional to the force that's applied. And we can't be forgetting the direction element to it there. And Newton 3 with the equal and opposite forces. If we look at application of those, as I've said, we need an application example of both at rest and uniform velocity, and also try to say what forces become unbalanced. So like a penalty, the ball is on the spot until the muscular force from the foot kicks it to make it move. With Newton 2, must refer to acceleration and the change of momentum, but also don't forget the elements. So again, going back to that penalty shot in football, we're looking at when the force is applied, the acceleration is proportional to the force that's applied to it, and it will take place in the direction that is hit. So hopefully for the football player, it will go towards the goal. And with Newton 3, it's the easiest one to remember that every action has an equal and opposite reaction. However, for example, make sure we state what the initial force is. So the dancer applying a force to the ground and where the reaction force comes from. So the ground will then apply an equal and opposite force back, and the dancer would jump in the air. Okay. With the calculations, I'm not going to spend too much on them. We just need to know them. We need to know the units of measurements. These two terms here, if you've done any maths or further maths, a vector has direction and a scalar is just a number that is used to talk about the quantity of something. So vectors, these are all vectors because velocity actually has direction. Velocity is bothered about in what direction of travel is something happening. We'll deal with that a little bit more next year. With the net force, again, links in a little bit with Newton's first law of motion. So if net force is 0, that implies that there is going to be no change to the motion, so Newton 1. So if net force is 0, something is either stationary, so it's not moving, or it is moving with constant velocity. So we need to be careful with that. So if we're looking at a runner who's running at the same speed, then the net force will be 0. Okay, so just because something's moving, it doesn't mean that it would have an unbalanced net force. If the net force is not 0, that would imply that there's an unbalanced force and the object is going to change its state. So remember the effects of force, the fact that force can cause an object to accelerate, decelerate, change direction, change shape, and a stationary object to get moving. So a little bit of application somewhere else there. With the net forces on the course, we are not bothered with looking at the combination of these. We're looking at like how vertical forces become unbalanced and what change that causes to vertical movements, and how horizontal forces become unbalanced and how that affects horizontal movements. So in terms of your arrows, the weight force, we must label it the weight arrow. So put a W on there somewhere, and it goes from the centre of mass to where the ground is, because obviously that's where the force is applied to. The reaction force comes from the point or points of contact, so there might be 2. If you're doing a handstand, there might be 2, and it goes opposite to the application. So as the weight's coming down, the reaction force will come back up. The size of the arrows is important. So if we have one point of contact and the weight for arrow and the reaction arrow are the same size, then there's no movement. If we're doing a handstand, then obviously the weight force would be from the centre of mass to the floor. Because there are 2 points of contact, it's important that the size of the arrow from both hands, when we add them together, equals that of the weight arrow. There's examples of that in the book, so have a look at that. With the horizontal forces, again, when we're looking at diagrams, try to label in which direction the movement is travelling. So maybe above the runner, you'd say, right, they're running in that direction. The air resistance comes from the centre of mass, and it goes in the opposite direction to the direction of travel, with friction coming from the point or points of contact, and that travels towards the direction of travel. And again, the relative size of those arrows will determine if we're in constant velocity, speeding up or slowing down. Okay. Factors affecting, what we need to know is not just what the factor is, but how it's applied. So if we're looking at ground surface, so a rubberized athletics track has a quite high level of friction, whereas an ice rink is a very smooth surface, has a very low level of friction. With the contact surface, if we look at a studded football boot, a very rough contact surface, that would increase the friction. If we look at a tap dancer's metal bottom tap shoes, they have a low level of friction because it's quite a smooth surface. With temperature, we're normally looking at the temperature of the contact surface. So if you think of Formula One drivers, they'll try and heat up their wheels. So if the temperature is higher, then friction will be greater. If temperature is lower, then friction will be less, and that would affect their ability to go around corners. And the size of the reaction force, like if it's a heavy object, is going to apply quite a large force to the ground. Therefore, a higher reaction force would increase friction. Similar with air resistance, velocity is what it is. Like we're traveling as fast as we're going to go. So in many sports, we're trying to maximize that velocity. So in essence, we're going to increase the air resistance. So that leaves us with our ability to affect the shape, the front cross-sectional area, and the smoothness. So with the shape, we're looking at kind of a three-dimensional shape. If you picture a track cyclist with the aerofoil helmet, quite a smooth, pointy helmet, that would be the aerofoil shape is aerodynamic, would reduce air resistance. Front cross-sectional area, we're looking at if we think of the outlined, shadowed surface of the object coming towards us. And again, if we look at track cycling, they get in that nice tuck position, their elbows inside like the outline of their body, so that they make that front cross-sectional area smaller. So a smaller front cross-sectional area would reduce air resistance. And the smoothness of the surface, again, like cyclists, skiers wearing lycra, smooth helmets, if the surface is smoother, again, it allows air to glide over it, reducing air resistance. With the technologies, we just need to know kind of what they are. So I'm going to quickly skip through them. So limb kinematics being looking at angles of joints, force plates looking at reaction forces, and maybe considering both those things, how we can limit injury, and look at the technique of running or throwing. With the wind tunnels, we see the skier here. What the wind tunnels do, they allow us to see how air travels past the performer. So if you can see the skier here, nice tuck position, head down, we can see air travels nice and easily past them. Okay, so that's going to reduce the drag and reduce the air resistance. Problems with all the analysis things are they're very expensive and very hard to get. If you go into stability, we need to know the definition of centre of mass, so the point at which the body is balanced in all directions. As a football, that will be in the geometric centre of the football, so right inside the bladder. In the human body, if we're standing in the anatomical position, so your toes forward, palms facing forward, arms out to your side, the male centre of mass is slightly above the belly button and the female's is slightly beneath. That's because males tend to have a higher mass on the top of their body, so the chest and the shoulders, where females tend to carry a little bit more mass around their hips. Okay, but if you're around the belly button, that'd be fine. And again, similar to the air resistance and friction, we need to know the application. So with stability, a heavier object has more stability. So going back to Newton's first law of motion, so if we're heavier, we have more inertia, so it's harder to kind of overcome them. So think of the front row rugby players, very, very heavy players, and they're hard to move. Height of the centre of mass, we're looking at the higher it is from the ground, the less stable it is. So if you stand on your tiptoes, you're less stable than if you're in a kind of a squat position. Base of support comes into how many points of contact and what is the outline that it's going to cause. So if you think of your dog or a cat, if you've got them at home, they have a rectangular base of support, 4 points of contact, and they're very, very stable creatures. If, as a human, we stand on one leg on our tiptoes, like a stork balance, we know that's a very, very small base of support. 1 point of contact, one tiny point of contact makes us less stable. And the line of gravity, if you can imagine the force, we're pulled to Earth through our line of gravity. So if which travels through the centre of mass. So if our centre of mass is directly above the centre of our base of support, we're very, very stable. So if that line of gravity intersects the ground in the middle of our centre of mass, we're stable. If it's to the edge of our centre of mass, we're less stable. If it's outside of our centre of mass, we're very stable. So in the sprint start, a sprint starter would have 2 hands on the floor, 1 knee, 2 legs. They've got 5 points of contact, quite a large base of support, a low centre of mass, and the line of gravity right through the base. On the get set position, they would lift their knee off the floor, their bum goes in the air, so the centre of mass raises, decreasing stability slightly. Their base of support will be the same size but with one less area of contact, and because their heads move forward, the line of gravity would shift towards the edge of their base. When the gun goes, they whip their hands off the floor, and one leg comes up, giving the sprinter 1 point of contact, a very small base, a much higher centre of mass because they're driving out the blocks, and the sprinter's line of gravity actually falls outside of their base of support, and in order to stop themselves falling over, that trailing leg needs to come forward and get back in it. Okay, so that's how we can apply those things. With the lever systems, quickly go over there, just remember 1, 2, 3, FLE. And the FLE, we're talking about the middle component. So a first class lever, the fulcrum's in the middle. Second class lever, the load is in the middle, and the third class lever, the effort is in the middle. It doesn't matter which way round the other two go, but just know that the mechanical advantage is when the effort arm is longer than the load arm. So the effort arm will be on the end. And then the disadvantage, the load arm is longer, so the distance from the load to the fulcrum. With a mechanical advantage, what that basically means is an object is easier to move, so it's more efficient, it requires less force. A mechanical disadvantage requires greater force, it's harder to move. However, when we do get it moving, we can apply more force. And if we go back to that, that means that a second class lever is always a mechanical advantage because the effort is always further away from the fulcrum than load. On the flip side of that, a third class lever, which is many joints in our body, is actually a disadvantage because the load is always further away from the effort. And for that reason, with lots of our our joints being mechanical disadvantage, that's why humans, we have quite a muscular build because we do have to overcome resistance. In terms of a first class lever, if you think of a seesaw would be kind of neutral because the fulcrum's in the middle, depending where the fulcrum goes closer to. So if the fulcrum is closer to the load and the effort arm is longer, that would make a first class lever a mechanical advantage. Whereas if the fulcrum was a bit closer to this end, to the effort end, then it would be a mechanical disadvantage. So hopefully that clarifies things. And yeah, email us if you've got any questions.